Hello, my name is Sasha, and I'm going to present my work on multifunctional electrolyte-gated organic transistors through material blending. So, organic bioelectronic devices are uniquely positioned to bridge the gap between electronic signal processing and ionic communication in complex biological environments. Among these, organic electrochemical transistors, or shortly OCTs, are particularly attractive for biosensing because they operate at low, biologically safe voltages and offer excellent operation stability in aqueous media. Now, in these OCTs, ions penetrate into the bulk volume of the film, yielding a very high signal amplification through volumetric doping. By contrast, in electrolyte-gated organic field effect transistors, or shortly EGOFETs, charge accumulation is strictly confined to the interface, enabling rapid, surface-driven response, but resulting in not very high amplification. So to overcome the limitation of traditional single material systems, which are typically restricted to a single operating mode, we present a simple, energy-efficient strategy based on material blending. So by co-processing an N-type fullerene mixed conductor, with either a semiconducting polymer or a second P-type mixed conductor, we can precisely tune the film's microstructure and unify these distinct mechanisms onto a single biocompatible platform. So in our first example, we blended an N-type fullerene-based organic mixed ionic electronic conductor named PRC60MA with a hydrophobic P-type semiconducting polymer, P3HT, that do not support the interaction of ions, at a 75-25 ratio. And we saw that the N-type fullerene provides a bulk OCT response through a volumetric ionic electronic coupling, while the P-type polymer enriches at the surface, enabling the P-type EGOFET operation through an interfacial charge modulation. And this allows us to selectively switch between a surface-driven and a bulk-driven transport within the exact same device simply by changing the gate bias. Now, in the second example, we achieved a balanced ambipolar OCT behavior by combining the same N-type fullerene, which we saw in the first example, with a P-type organic mixed ionic electronic conductor, a polymer named P3MEEET at a 60-40 ratio. And this produces a homogeneous microstructure where both the components undergo bulk volumetric doping, and as a result, the device can sense both cations and anions, demonstrating an adaptive bioelectronic functionality and multi-ion detection across different ions such as chlorides, nitrates, potassium, and calcium. So overall, this work shows how strategic composition control let us bypass complex multi-layer fabrication and engineer a truly multifunctional bioelectronics. And I invite you to discuss my work with me at the upcoming IMRS conference.